All right, so there's two different types of sort of general categories of electrochemical cells. There's the galvanic cells and there's electrolytic cells. And the difference there is just whether or not they're spontaneous. So galvanic cells are those that are spontaneous, where they have a negative change in free energy for system. Electrolytic cells are the opposite of that. They require energy go in. If you have something like a battery are just two half cells, two half reactions encapsulated in a structure. And rechargeable batteries specifically operate both as galvanic and electrolytic cells. They operate galvanically when they're discharging, when they're powering your device. They're just naturally reacting and then releasing electrons that we harvest as current to power our devices. And then when they have completely run, so we run out of one of the species, if you have a limiting reagent, then they need to be recharged, meaning they need to go from their low energy state back to their high energy state. How do you do that? Well, you got to put energy into the system, and then you're running it as an electrolytic cell, and you're running those half reactions backward. If you have a non-rechargeable battery like the old NiCads, then it's just a galvanic cell. It can only run in one direction, in a spontaneous direction, and for reasons beyond the scope of this class, it can't run in the electrolytic reaction without destroying the battery. So the purpose of this video is to walk you through some galvanic cells, some of the formalisms, how we think about the reaction chemistry, how we document what the voltage change is going to be, how we determine if it's going to be galvanic and what direction it's going to be galvanic, and then we'll talk about the shorthand that we use to describe a cell. So the cell that we're talking about is this one here. It just comes straight out of your textbook. So you've got two chunks of metal. You've got a cadmium foil electrode and a silver foil electrode, and those are both connected and hooked up to this thing called a potentiometer, which is just many of you probably have seen this before. It's just a multimeter or voltmeter that you would have you could buy in a hardware store. In terms of convention, and this is not just in electrochemistry, this is just in general. Like if you open up your car, if you have a car, if you ever opened up a car before, you'll see that the red wire on the car battery goes to the positive terminal, and the black wire goes to the negative terminal. That's just general convention in this country. We deal with black, negative, red, positive. That's going to be the formalism here, although that's not crucially important unless you're doing an experiment. And even then, it's not crucially important, as I'll talk about later. But that's the general convention you'll see, just so you're aware of it. Whenever you have a cell, an electrochemical cell, you have to have two half reactions. Because if you're taking electrons from some species, those electrons have to go somewhere. And that's always going to be true. You can never have just one half of a reaction. And so in this cell, we've got two different reactions. You've got cadmium ions, cadmium 2+ in solution as cadmium nitrate. That's the salt that was added to the solution. And then you've got silver ions that came from silver nitrate. So you've got both silver 0, which would be the metal, and silver ion, silver plus, and you also have cadmium 0, which is cadmium metal, and cadmium 2+. So you have both of those in the system. So I'll write those out here, and this is just in one possible direction. So we have the silver being reduced to form silver 0, and we have the cadmium then in the opposite direction being oxidized, where it's losing 2 electrons. You always have to have an equal and opposite effect. And you also, if you remember back to balancing redox reactions, you always have to have the same number of electrons being transferred in both halves of the reaction. I will upload if it's been a while since you've balanced a redox reaction, I'll upload a video from Chem 107 that I use to teach that. It's been a while. It's a little bit tricky. We're not going to do a whole bunch of balancing in this class, but it might be helpful just as a reminder. Anyway, when you add these two together, of course, the electrons have to cancel. They have to be the same. If they're not, then that's a red flag. When you add them down, you get this system where you have silver ion and cadmium 0 reacting together. Silver gets the electrons from cadmium, and then that yields cadmium 2+. So always in a total full electrochemical cell, it's going to be comprised of two half cells. We sometimes call those half reactions too. And you can couple any half cells together. It doesn't matter. but it may not mean that it will spontaneously go. Spontaneity means that the reaction will occur in the direction that it is written. It's important to know that in terms of reversibility and electrochemical reactions, whatever delta G you compute for this forward going direction, say we calculate this as a minus 100 kilojoules per mole in the forward going direction, what that literally means is that it's spontaneous in the forward direction by 100 kilojoules per mole, and it's non-spontaneous in the reverse direction by exactly the same but opposite. Right? These are just simple reversible reactions. You think about it in terms of the voltage here or the delta G here. If you're starting at one point, you're ending at one point. The difference between those two states is the difference in free energy, and going backwards is the same difference but the opposite directionality in terms of the energy flow. And so it's important to recognize that the sign difference is simply stating the reverse of that. So if you have a galvanic reaction in one direction, by definition, the opposite direction will be electrolytic. It's impossible to have a galvanic reaction in both directions. So for this reaction, we're not computing whether or not it's galvanic. I'm just writing it out for you as in the galvanic form. So this is naturally spontaneous in the direction that I have it written. So that means spontaneously, if you have silver ions and cadmium 0, then those two things are going to react spontaneously to form these two other species. The way that we would use the shorthand or write the shorthand for a cell like this would be like this, and you might have seen this in Chem 108, or you should have seen this in Chem 108. We always write this in the direction that electrons will flow, and so from left to right, electrons are flowing in this direction. This is always going to be true, and so this can be helpful in understanding this. So what that means is we have cadmium 0, the metal, which is, I keep saying 0 because these are zero valence states, all metals are. The same is true for silver. And what we have in the reaction is we're starting with cadmium 0, and it's giving away 2 of its electrons via this half reaction to silver plus. And so the electrons are being removed from cadmium, and then in this state, cadmium is 2 plus, so you've oxidized the cadmium, and you have in this state, silver plus, those electrons are going to the silver plus, and you end up with silver 0, which is what we have in the final state. And so you're always starting with the fully reduced species to start with, and you're ending with the reduced species in the end. So the direction or electron flow will always be left to right. Which means that the thing being oxidized is always going to be the thing on the left. So this would be the oxidized species, and then this would be the reduced species, simply by requirement. If electrons are flowing left to right, that thing is always being oxidized, and the thing on the right is always being reduced. Then in terms of nomenclature here and the details of how we represent this, vertical lines here are phase changes, or phase boundaries, I should say. Either one, those are equivalent. So you got a phase boundary at that vertical line, and you've got a phase boundary at that vertical line. So what that means is you've got the cadmium metal here, that's a solid, and then it's in contact with the solution around it, which contains both cad nitrate and silver nitrate. So we put a physical vertical line there to denote the phase change from solid to aqueous. Inside that next phase, we use a comma to denote that both of those species are present in the same phase. So we have both cadmium nitrate dissolved aqueous and silver nitrate dissolved aqueous in this system. To be good here, we would include the phases aqueous, just to be fully comprehensive. And then, as we're sort of moving from left to right, from cadmium, we moved from the solid into the solution, we denoted that solution, and then from the solution, we moved to the next solid, which in this case would be silver solid. And so, of course, there's another phase boundary to note the difference between the aqueous phase and the solid silver phase. And so the way that I like to draw up these reaction, or these shorthand schemes to describe the electrochemical cell, is to first have my balanced electrochemical full cell reaction in the direction that's spontaneous, which we have. I'm just telling you that. You don't know that necessarily. You don't have the tools yet, or at least not enough information to determine that. But I'm telling you this is the spontaneous direction. And then you're just going to write them in the direction that electrons will flow from cadmium solid, phase boundary, aqueous solution containing both salts, phase boundary, silver. And so you should be able to go either way, either have a cell that's drawn for you or a cell, even just the half reactions, and then be able to write the shorthand, or you should be able to have the shorthand and then write up the relevant half reactions, the full cell reaction, and then sketch up a cartoon of what that cell might look like. You should feel comfortable going both ways. Okay, so how do we actually know that this thing is spontaneous in the direction that it is written? Well, we need to understand the relative energy levels of each of these half reactions. As I mentioned before, and we'll talk in greater detail about this a little bit later, either in this series of videos or the next chapter series of videos. Just like free energy and enthalpy and entropy are all related to some arbitrary zero value, the free energy, or the electrochemical potential, or E, for any half reaction is also related to an arbitrary zero value. You can see that zero value on this list of standard reduction potentials. That that half reaction that we just arbitrarily chose as 0 in terms of voltage is the reduction of protons in water to make hydrogen gas. You can see that that's at 0 volts. Everything is with respect to that. So it's either higher in energy or lower in energy. Remember, positive values are actually lower energy with potential. Negative energy, or negative potentials are higher energies, meaning it takes more energy to, say, reduce lithium to lithium metal down here at minus 3.05 volts compared to reducing fluorine. And that makes sense because fluorine is the most electronegative atom on the periodic table, so tacking on 2 electrons onto that to make fluoride, it doesn't take much at all, because that would complete the octet and make it really happy. Okay, so more later on standard reduction potentials, but in order to determine spontaneity here, all we need to do is figure out the delta E. What is the difference in energies of these two half reactions? And then we use the sign to tell us whether or not that's spontaneous. If you recall, the relationship between free energy and the voltage change or potential change is delta G equals minus NFE, the key or operative parameter here being this minus sign. So remember, the spontaneity clause for free energy is that if it's a downhill reaction, then that means it's a negative free energy change. But since potential is sort of flipped in its axis, then a spontaneous reaction would also have a positive potential change. So spontaneous would be negative, non-spontaneous would be a positive delta G and a negative E. So that's what we're going to use. So we first need to compute what is the delta E. As I mentioned before, this is actually a delta here. What's the change in energy for the full cell between the two half reactions? And then we'll use that to assert or assess whether or not this thing is galvanic or electrolytic. So I've highlighted the two half reactions here. So we've got silver plus an electron makes silver. That's at 0.8 volts. Remember, these are what we call intensive properties. So the standard reduction potential here, E naught, which is its relative energy of that half reaction, it's intensive, meaning it's specific to the reaction and has no bearing on how much or how many of that reaction runs. So I say that just because in this case, our half reaction required a 2 to balance out the number of electrons, and our cell potential, our standard reduction potential, this is E naught, so this is at standard temperature and pressure. That's what the naught is there. That's 0.8, but we don't multiply that by 2 because it's an intensive property. It doesn't matter if we have 1,000,000 silvers or 1 silver, it still takes the same voltage to drive this reaction. So it's an intensive property, which is different than energy, at least in terms of Gibbs free energy, which is an extensive property, which of course is in units of kilojoules per mole. So that means that I'm just going to write up positive 0.800 volts for this particular cell reaction. Oops, I forgot the 2 electrons here. And then cadmium 2 plus is minus 0.40 volts. But notice that all of the reactions, the half reactions that are written in this table and in any appendix or anything you look at ever for standard reduction potentials, these things are called standard reduction potentials. So every half reduction is written as a reduction. It's going to be some species plus electrons because it's a reduction step, even if the reaction that you're interested in is the opposite of that. And in this case, that's true, right? We have cadmium 0 going to cadmium 2 plus, which is the opposite of the reduction because that's an oxidation step. So there's sort of 2 different ways to account for this. I'm going to write this up here as minus 0.40 volts. Just as it's written in the standard reduction potential. So I haven't done any tricks yet. I haven't done anything to change this up. Because these are intensive properties and we're adding the 2 half reactions together to get our full cell reaction, right? That's an addition. Then we will also add these 2 steps together. The issue here, though, is that we have a reaction that's running in reverse. And you've looked at this, right, in a Gen Chem course. If you flip the directionality of a reaction, then you're flipping the sign of its respective intensive property here. So that means we would flip this, and if we flip the half reaction, that means this thing becomes positive. And then we can just add these things, and this becomes a positive 1.20 volts. There's a couple other ways. I mean, there's several ways to think about this, and everybody has tricks. I like to think about it in this way, just because it's easy to keep track of. You could also, if you didn't want to add these, the other way to think about this is because you originally had a negative value associated with the 0.4 in the reduction direction, but your half reaction is in the oxidation direction, then you could multiply this thing or subtract this thing because you have essentially multiplied your reaction by -1 to flip it. And so that it equates to the same thing because now you have a minus and negative, which is essentially the same thing. You can do it either way. I think what I'd like to say, though, as an electrochemist, is this gets a little bit conflated. If we do just simply add a positive sign here and flip the sign, what you want to be a little bit careful of is that this reduction potential here, this is the E0 of cadmium 2 plus 2 electrons makes cadmium 0. It's got an E0 of minus 0.4 volts. What that means on a number line is that if this is potential, negative being more energetic, this is volts. If you've got, if we sort of think back to this, the previous analogies that we talked about, where we have average energy in your electrode, which would be this blue thing, and then you have the energy of your species that you're oxidizing or reducing. If that process occurs at minus 0.4 volts and you raise, say, the energy of your electrode to 0.4 volts, thermodynamics would say that we could reduce that species. So we're not going to talk about kinetics now, but that's true, right? If we keep pushing this more and more negative, then cool, we keep reducing that species. That's at minus 0.4 volts. So as long as your electrode is at minus 0.4 volts, then this is true. This gets a little bit complicated, though, because if you lower your voltage below minus 0.4 volts, then you start to draw electrons back into the electrode via an oxidation step. But that's, again, at minus 0.4 volts, not at positive 0.4 volts. So just because we flipped the directionality of the reaction, that positive sign has no physical bearing in reality, because it's not like then you need to get down to positive 0.4 volts before electrons can then transfer over, because that means that there's this arbitrary space of 0.8 volts where reversibility doesn't occur, and that makes no sense at all. And so that sign here, if you do flip it to positive, which I do, even as an electrochemist I do, I always keep in mind that that has no meaning, because really it's still minus 0.4 volts for that reaction. And if I go more negative than 0.4 volts, then I'm going to reduce that species. If I go more positive than 0.4 volts, I'm going to oxidize that species. So just keep that in mind. Hopefully that wasn't too confusing, but often this step becomes confusing simply because people aren't aware of how this sign change has significant impacts on the fundamental understanding, the reversibility of these chemical reactions. Okay, so last step that I want to mention, which is sort of the final punchline, is we did all this stuff, right, and we decided that this thing was positive 1.2 volts, and we said that negative delta G, remember this relationship, delta G equals minus NFE, so if we've got a positive value for our E cell, we call this E cell, which is the same as delta E cell, they're the same thing. That's a positive value, which would mean we'd have, in this case, a negative delta G. So the reaction that I have written is spontaneous in the direction that's written. If I were to reverse this reaction and write this up as the exact opposite, so that would be cadmium 2 plus 2 silver makes cadmium 0 plus 2 silver ions. We would say that's non-spontaneous, that's an electrolytic reaction, and that would take minus 1.20 volts in order for us to drive that reaction. Okay, so with the galvanic cell that we have drafted here, there's some fundamental flaw with how it's constructed, and maybe you've already seen this and identified it. Why, if we connected the cell like this, why would we observe no current flowing in these wires? That's the question. Pause the video, stare at this for a second, and after all of this, after telling you everything about this galvanic cell, it's spontaneous, it will occur. Let me tell you, it has nothing to do with kinetics. That's a separate discussion. Why will no current flow in the system, even though we've said that there's going to be a 2-electron transfer in this cumulative redox reaction? Think about that for a second. So the reason why you won't see any current flow is because of a design flaw in this cell. This cell itself, there's no reason, right? If this, let me take a step back here. If this is the reaction, this is the full cell reaction where you have silver metal reacts with cadmium 0 reacts with silver ion to produce these species. You've got silver ion here, and you've got cadmium metal here. What is causing, what would stop these two things from just reacting themselves and exchanging electrons directly in solution? There's nothing, right? There's nothing that would cause these two things to separate. In other words, there's nothing that's actually allowing the electrons to move up through here, because the electrons are going to be exchanged directly at the interface of these things. So the reactions are occurring directly in the system without being forced through the circuit, right? That's an important design flaw in this electrochemical cell. And so in real cells, what we need to be able to do is separate the two half reactions physically so that we can still leverage the difference in voltage, which means that there's a difference in energy between those two half reactions, but we physically isolated them so that they can't just react together in solution. If we don't isolate them, there's nothing stopping them from just reacting simply based on the fact that they have a negative delta G. They're just going to do that. So in designing functional galvanic cells, it doesn't mean that this won't occur, right? This is why pipes rust in your house. This is why all sorts of things spontaneously electrochemically occur is because there's no separation of the two cells. But if we want to use this to either measure something or to, say, do work, which means we need to have electrons moving externally through a circuit, which is how a battery works or a fuel cell works, then we need to physically isolate these into two half cells. And so you may say, oh yeah, I remember this thing called a salt bridge. That's where we're going with the next video.